Greetings, I'm Bill Wagner.
And I'm James Sturdivant.
And now we're going to look at some of those encapsulation practices inside the core .NET framework. So we're going to spend most of our time on this module looking at code, looking at the code that you use every day as a .NET developer, and look at how these practices apply to that kind of a production code base. So with that, what we're going to do, we're going to start by looking at the string builder class. In this particular demo section, we're going to have 5 different sections. We're going to look at string builder. We're going to look at 2 of the classic collections, hash table and array list. For those of you that are familiar with generics, we chose those 2 because we haven't covered generics yet. After we cover that module, we'll update this a little bit to look at those generic classes. Then we're going to introduce a lab for you, and we'll come back in a separate clip and talk about one possible solution. So let's now begin with that first section, where we're going to dive into String Builder.
And I was really excited and impressed that you picked String Builder, because it's a library that we use and that you're probably actually very familiar with. And when we look at the API, it's a really simple API that we can easily use and build our applications quickly with, especially around when we're working with strings. But when we dive into the code, we'll find that the actual implementation is incredibly complex. And it's really going to demonstrate how encapsulation works best.
Right, that's one of the things that I wanted to do. So before we dive right into the code, there's a couple different websites that I want to point out to people so you can follow along, load the code yourself, walk through it, and use some of the tools that we're using. So first, I've got on GitHub here, if you go to github.com/Microsoft, you're going to see a list of most of the .NET libraries that have been released as open source. I'm not going to scroll through all of these. There's 13 different pages. Another one to go to is if you go to microsoft.github.io, you'll find a list of all the repositories that the Microsoft .NET ecosystem is involved in. And again, a lot of these aren't necessarily ones that come out of Microsoft, but Microsoft is supporting and helping to work with. For instance, some of the Node.js work is not a Microsoft product, but they're working on and actively doing some of their own contributions too. The particular one that we're going to look at today in terms of these 3 classes in this particular code review is the Core CLR project. So if you go to github.com/.net/CoreCLR, that's the repository for this code. So if you want to clone it from here, you can see links on the right on the screen here. So github.com/.net/CoreCLR. And if we look on the right, we can see areas to clone or find anything here. If you're used to GitHub, you can search here to find different classes that you think might be part of this project. So if I wanted to do the review right on GitHub, if I were to search for String Builder, I can find all the different places where it's used. Now, because it's used a lot, I'm finding 104 different code results. One of them happens to be the class itself, so we can see exactly where it's implemented and how it's put together right here on the web. Instead of that, though, we cloned it to the local machine here, and I'm going to load it in Visual Studio because that's the tool that we're most used to, and we've got a little bit richer set of tools to work with. So first, as James mentions, if we look at String Builder, we'll start by looking just at its API. So this is just the String Builder class on MSDN. And we can see we've got a number of different constructors. When we mentioned earlier, we might want to think about trying to minimize the number of APIs we have. But they do have reasons for these, some for performance considerations that were added over time, and some as the class has grown. We've got a few different properties to it, total of 4. And then we get to the public APIs. A lot of them are overloads of an append method, so we can add new content onto this string. A few others, we're going to append formatted content. We can clear it out, copy things. Some of the things that it's inherited from the object class we have to work with. Can insert in the middle of it, basically modify this string that we're going to be manipulating. And then finally, we have a toString method that will pull out a static string from this string builder. So we've got, as James said, fairly simple API that we'd be using to build our applications with.
Yes, and the reason we might choose to use the string builder class is if we have, if we're modifying a bunch of strings together, that can be very expensive for us to do, and it could cause some performance issues. And so if we're going to be modifying a string and appending and building up that class, or building up that string as we go, this is when we'd use the string builder. So let's go ahead and dive into the code.
Right. Okay, so I've got the project loaded in Visual Studio. And the easiest way for me to find the string builder class is I'm just going to do a search anywhere in this project for string builder. And I'm going to find a whole lot of places, as I said. I'm just going to pick the first one. And this is declaring a string builder class. And now if I press F12, it's going to take me right to that class. I'm going to switch into full screen since we're really just going to be looking at code. And for those of you that are unfamiliar with it, that quick launch bar up in the upper right in Visual Studio, I can type anything that relates to any command and quickly get that command to execute. I can never remember the keystrokes for full screen, so I usually just type it up there. So we look at the class. Inside here, you can see we've got a number of internal variables. So there's some other classes apparently that would work with string builder in order to do its work. We've got some constants as far as just how big is the capacity. Looks like it starts at 16. We've got some things in terms of how do we work with some of the some strings that we've defined for other things that get stored that maybe can get configured later. Now if we look at our constructors, we're going to build this thing with some kind of a capacity to it. And one of the things they're doing here is they're chaining from one constructor to another. So they're going to try to minimize how many times they write the initialization code and still give people using it a lot of different overloads to be able to construct this object. But they're going to share a common implementation. As we keep going down, we'll get to that common implementation. You can see we start with, okay, here's a bunch of validation. Okay, capacity has to be greater than 0 or equal to 0. Length has to be start at least 0. My initial index has to start at least 0. And now we're going to start initializing this thing. So we create an empty string if we need to. We start creating some storage for all the characters. And now we start copying some things in if we need to. We're going to copy some of these characters that came in from this string that may have initialized it. We're going to use unsafe code to try to copy these characters very quickly. So that's quite a bit of work just to build the initial string builder, right? So we've already hidden all that complexity for anybody trying to use this code.
Yep, and down there you can actually see that they've defined and they're using a method called thread safe copy. And this is actually doing some copying directly into the memory space that they've allocated. And if we take a look at thread safe copy, we'll see that we're going to be using that piece of code throughout the entire application. Or
throughout this class, because it's private.
Yeah, sorry.
Yeah, that's okay.
Throughout this class. And so you can see here that it's a private method. And if we were to use the string builder, you wouldn't actually have access to that thread safe copy. And here you're also seeing that it's being used, as Bill has pulled up this find symbols, you can see it's being used continuously throughout the entire class. And so this is a great way of doing some encapsulation inside of your class and only and not leaking that implementation details out to the outside, to the classes that are using it.
Right. And now, so we can construct it. We've built some of these buffers. We've done some of that work. The other one I want to look at is I want to look at least one of the append methods. So this far right combo box will take me to different methods inside a particular class. So if I look up here at, let's append a string, because that's one of the ones that pretty easy to understand. It's just going to take a string that we pass it in, add it to the current string builder, and we now have a string builder that's got a larger internal storage based on whatever string we've just added to it, right? So we're only going to do this if the value isn't null. And now if we look at what it's doing, what we're going to do is we're going to grab some things onto, we're going to allocate a set of the string, make sure that our storage is big enough to accept the string that we want to append. If not, we're going to have to go grab some new storage, copy things into that storage, and then set to where that storage now contains the new set of characters. And that's done by this, can be done by this append helper, which we dive into. And to see, that's basically calling that append, which then adds new characters back onto the characters that we're putting in place.
And what's the key stroke that you did there to pull up that little helper dialog?
If you pull up Alt F12, that gives me a floating window at the definition of wherever I started. So here's where we're going to start to set it in place. You can see the comment that says, this case is so common, we're just going to optimize it as much as we possibly can. There's that thread safe copy again. We're going to pull this in place. We're going to copy those characters right into the storage of that internal array of characters that we've added in this class. Otherwise, if it's not big enough, we're going to copy the first chunk, then we're going to grab some more storage, we're going to add another chunk, and then we're going to keep right on going. Okay. What's interesting about this is what's actually happening is it's not continuously reallocating the array. Once we've filled up one array of characters for some logical size of a string builder, instead of grabbing a new array and then copying everything that we've already built and then making a bigger array, it's going to keep making these chunked arrays of characters, storing the string as it builds it, and then finally we'll look at the last one, which is toString, which pulls everything out, which will then pull the characters out of the string and give us a string with everything that we've used to construct it. So the last one that we want to look at is this toString variable method. Let's do that in the main window here. So if we go look at toString, what we're going to do is we're going to do some validation. Okay, then we're going to allocate a string of a current length. Okay, this fast allocate string. If we look at that, that's internal. We can only get at that because this code is part of the same core CLR assembly as string. So that's not a public method. That's one of the things that it's able to do just internally. And then what it's going to do is it's going to take each one of the current chunks in the string builder and keep appending those characters into the source for that string. And again, here it's going to leap into some of the things inside the string itself and do some internal things that we can't get at to as users of the .NET framework, but the string builder can, being internal. So there's quite a bit of complexity that I find that's being hidden inside here from us, which I really like, right? As we mentioned, what we're really looking for here is this class is easy to use. You know, James mentioned that. I've now mentioned this. It's simple to use. Allocate a string builder, append things to it, pull out a string. That's really all we have to do. And there's a lot of this work inside to try to keep that very performant. This idea of having different chunks that it's going to allocate internally. You know, it may or may not have been the first design they came up with, right? Because they may have just started saying, well, we'll have one array and we'll keep adding characters. And then they saw there may have been some performance implications there. So they could change that internally and come up with this faster algorithm to then be more performant without changing any of the external access needed, right? That's just a theory. I don't know. I've never seen the earlier code before it was open sourced, but that's just one possible thing that happened. But the idea is that the design enables that to take place, right?
Right. And so they'll also be able to change some of the implementation details later on. So if for whatever reason they move to another platform or they go somewhere else, they'll be able to actually change those implementation details while keeping the public interface the same. And that's a major advantage to this encapsulation that we're discussing here.
Right, and some of that may have already happened. I didn't see anything in this particular class, but the .NET framework now runs on different Windows devices. It runs on your phone, which has a different processor than our laptops here, or our tablets. The ASP.NET vNext project is running on Linux, also possibly a different processor architecture. So they may have changed some of the internals to support that. And those are all possible now because of that encapsulation. We don't need to see that ourselves.
Right. So up next, we're going to be taking a look at the hash table. And a hash table is a associative array, which allows us to access the information via a key. And the reason we want to do this is because if we have a large number of information that we need to store, but we want to be able to access it in a single in ON time frame, which means that we want to access it at the rate, at a consistent rate, then we'd start to use this key. It's very similar to a dictionary if you've used that in the past.
Right. Or if you've used JavaScript, the anonymous types in JavaScript that have key value pairs. That's a form of an associative array.
Yes.
Mm-hmm. Right. So again, I'm going to do this the same way. Let's look through and see exactly what we can do with our hash table. If I look at that class, and again, we're going to stick with the non-generic version right now because we haven't covered generics. We'll look at dictionary and such later in this course. And again, our hash table class, we've got different constructors to be able to put some things together. We're seeing some interfaces there that we'll cover more later, but the idea that I can initialize this and put some elements in the dictionary. I can do some things to decide how I want to check for equality, which is going to be important in how we work with these associative array. Are these keys actually equal? Right, and we may need to override that depending on what type we're using as keys. We've got a number of different properties. Notice that, again, this is code from .NET 1.0, so there's a couple of them that are obsolete, and we can move back on those later. We've got some ways to get out a different element. We can get at an item, which is an indexer in C# by referencing its key. We can get the entire collection of keys or the entire collection of values. And then again, we've got a set of APIs that allows us to add things to the dictionary or to the hash table to be able to see if it contains something, copy it to one or another place. We can do an enumerator to be able to look at all the elements in a dictionary, get back key value pairs so we can look at both. And we can remove an element, and we can then some of the extension methods we're going to leave off on the side at this point because they're not actually part of this particular class. But we've got, once again, a relatively simple and easy to use API. I've got keys and I've got values. I can add something to this hash table by specifying a key, where I want to store it, and a value, which is how I want to get back, or what I want to store associated with that key. I can enumerate those, or I can find a single value out of it, work with those and bring particular values out of that hash table. And again, that implementation is now going to hide quite a bit of those details. So let's look at how that's put together. We'll go back over to Visual Studio. And again, I'm just going to search for that hash table class, find an instance of it. And again, I can find it just anywhere if I find an instance of a variable. It turns out it looks like I've actually found the implementation of it immediately. We'll go back into full screen again, concentrate on the code. Again, we've got a fair amount of some implementation notes. You can see that once we get to generics, they apparently grabbed the source directly from here. So if we find a bug, let's make sure we fix it in both places. How they're doing the hash algorithm, so that we've got different, this is a double hash algorithm, so that each bucket can contain either 0 or 1 element, and so on. We can read that yourselves as to how the hash table finds something when we hit something and we have a bucket that's a collision. So what happens here is when we try to build a hash table, we have a function that generates a number based on the properties of the key. So a bucket may actually have more than one value. Like let's think of strings, okay? This would be a very bad hashing algorithm, but this is the idea of what happens. Let's say my hash function for strings were to use the length of the string, okay? So all strings that had one length would all be in one bucket. All strings that had the length 5 would be in another bucket. So then if I wanted to find a key, I could take the key, see how long it is. I have the bucket and I know what values are there, and I could find that particular value. That's a bad hashing algorithm because we'd really want it to be distributed evenly over all numbers. So the actual hash function for a string is noticeably different and we'll get a better even distribution. Okay, and then once we do that, then we have to find the next algorithm. So there's a lot of computer science into how this is going on. You can see there's a good page and a half of comments here, and I've glossed over a lot of it. That's kind of the point. We're looking at this encapsulation idea. I can use the hash table without remembering how it's all implemented. Got some of the things where how are we going to store some of these constants, work with how a bucket works. You can see we have this private structure here. Once again, like we talked about in the PowerPoint, I can put together something that's hidden that only hash table uses. So hash table uses this bucket idea that has a key, has a value, and has its hash value. It stores the hash code. I have a bunch of buckets. So I have this array here, array of buckets is going to store these things here, which have these key value pairs. So for every bucket in that array, it's going to match one of those hash collision values or hash code values, and then it's going to have a set of key and values in place. We've got our count, we've got the occupancy, total number of collisions, how many things we're getting. And then we're going to start building a lot of internal stuff in terms of how our comparers are working to try to find where something goes in the hash table. Now we'll go ahead and put things together. You can see there are some properties that we can use to put together a hash table as to what its capacity is, what its load factor is, which is how big buckets should be before we start splitting them up. There's a lot of different computer science algorithms in terms of building a good hash table. These are all in place down here.
And one thing you note is that when you're using the hash table, you actually don't need to know all these computer science techniques to make sure that this is fully optimized. And so that's a great way to demonstrate how this encapsulation is being used in practice inside the core CLR.
Right, and there's a few things that are documented in the public API, which you mentioned that there's order and log n to get elements out of a hash table, because that's how we go find them. There's order n to enumerate everything in a hash table based on how many things you have in the table. Those kinds of things are documented, and the algorithm, that complexity, ensures that those performance metrics are met. So let's look at just how do we get at an object for something. So if I were to come down here into the hash table, if I were to look at that item property, which
it's in the index there.
In the index there.
This is a great example of where we would actually use a property to hide some of the complexity of when we actually get the item from the dictionary. There's quite a bit of logic to find the hash table, to find the hash, to make sure that the keys match, to make sure that the values match. Mm-hmm. And then finally, if all those things match, then you can actually retrieve the value out of that bucket that we saw before.
Right, so briefly let's look at that algorithm. Here's the indexer. So it's a method called this in C#. It takes in a key, and it's going to return the value. So we've got a few, it's going to have a getter, checking some of our parameters. If the key's null, this makes no sense. Okay, now we're going to look at all the buckets. We're going to find the code for this particular key based on the current number of links in the bucket, a seed, and our increment value. We're going to go find if it is in one of these buckets. You can see it has 3 steps followed by a numbered list of 4 items. So maybe a little comment creep there, but calculate the hash and find the slot number, compare the hash code. If it's equal, go to step 3. Otherwise, compare the key. If they're equal, go to step 4. Otherwise, we didn't find it. Step 4, return the value obtained in the bucket. Okay, great. So now we'll go through and try to implement that. We're going to try to do the read, find those things in here, spin up to see where else we're running, see if we find the hash code. This part here is noticing that if there were collisions, we said up at the top where we were looking at that bucket structure, that it was going to set the sign bit to be able to say, oh, this is going to equal something, so then they equal, we found it, right?
Yeah, and so what's great here is, Bill, if you scroll up just a touch there, you see that there's a point where they have, if you have multiple threads running and trying to access this, you'll run into some contention, and they're actually releasing the thread so that other things can run, so that the CPU isn't being used. And so what's great here is that you don't need to worry about that complexity. You get that they found that that was a problem once they started using this, and they started implementing it in complex applications, and they were able to then add that into the get method of the dictionary, or the hash table.
Yeah.
And so that was something that they were able to add afterwards without breaking the interface.
Right. So then, again, a reasonably large algorithm to be able just to get something out of this. But again, very, very highly optimized to meet those performance metrics. And the setter, to be able to get at something, is going to end up calling this insert method. So we'll hit F12, dive into exactly where that is. And again, a private method to do an insert. We've got our key, we've got our value, whether or not we're going to add to it or only replace. So there's a couple different bits of semantics there where I can add something to a dictionary depending on the API I called, or only replace something, which should throw an exception if I don't find that particular key yet. We're going to look through once again, try to find where it should be. And once again, looking at only one writer thread going, so we may have some concurrency issues here. So we're going to look through some of these things, dive through, try to find where this should go. And again, we've got a good 50 to 100 lines of code here trying to dive into some of these particular bits to see where should this element go in this hash table. Eventually, if we find it, this section is if it's available if we didn't find it. Or if we did find it, we're going to write it, we're going to set that value. If we're not doing an add, then it has to only be, or we're able to do an insert as well. And once again, we're going to update that bucket, set the value to it. Roughly about 100, 150 lines of code to go just do what we make in one call, which is I want to add something to this hash table.
So that's a really great example of encapsulating all of that logic and all of the performance implications that they have when they're working with those things. So up next, I think we're going to take a quick look at the array list. And an array list allows us to be able to add items to a list, adds items to a list, and we are able to grow that list dynamically.
And again, the hash table is one of the details we glossed over looking at some of these methods. The hash table will grow as well. We can add new items to it, and it'll grow its storage as needed. So if we look at the documentation for that array list class, again, it's the non-generic version. So I've got 3 constructors. I can just create an empty one. I can create it and say, put all of these items in it. And I can create it and say, reserve this much space to begin with. I've got some properties that gives me some idea just how big is this thing, what's in it, what's the count, how many items are actually stored there. I can get or set an element at a specific index. And I've got some methods where I can do some add. I can add a whole range of items. I can search for something to do a binary search, which will only work if it's sorted. I can remove all the elements. I can do some copy. I can see if something's in there. And again, do some of the standard enumerations to work through some of those. Find where an object exists, if it does exist. Insert instead of just adding. Remove items from it. I can reverse the whole list. I can sort it. I can turn it into a fixed size array. And I can trim it to a certain size. Note that with there's both this insert and add again. And here they're going to be implemented a little bit different internally because of the performance metrics. If I want to add something, that's just putting something on the end. If I want to insert something, I'm going to have to open up a slot somewhere, move everything else over one, and then put the new element in place. So now if we look at how that's built, again, we're going to just search inside this particular solution. We're going to look for array list. And again, we're just going to find something that has the type. There we go. I think I actually found the internal class itself, or one of the constructors. So again, public class implements a couple interfaces, which we'll talk about later. You can see that its storage here is an array of objects, okay? And it's got some other properties, internal members, that give us an idea of about its size. I'm not sure exactly where version is used, unless that has to do with how it's storing things and serializing itself. This private object sync route is going to be used to lock the connection when we have multiple threads possibly accessing it. We've got a default capacity, and we're going to give a static idea of something that's just empty. And now you can see we're starting to build some of the constructors. We can see we've got setting some items to this empty array, which is this read-only thing that's just empty. We're going to be able to have a capacity, so we're going to say, all right, I'm going to build a certain set of, a certain class that's got, or a certain storage internally matching that capacity. Here we can see one of those performance improvements already. Notice that anytime the array list is going to take the size of 0, it's using this default read-only empty array. So this class is only ever going to allocate an array of size 0 exactly once. It's going to initialize this, put it together, and then anytime it needs an empty array, it's always going to use that same storage. So it avoids allocating that rather common empty use case often by always reusing the same storage. So that's going to mean that this class has less of an effect on adding and releasing memory and slowing up the garbage collector than it might otherwise have. So creating empty array lists is just going to reuse the same object over and over. We can construct it with a collection, pull things in place. Now we can read what that capacity is, get at its count. And again, the things that I really want to look at here, we're going to look at that append method, or that add method. And here, this is a relatively simple method, but it's going to use a couple things internally. So if size is the current length of the array, so if the size of the array, or if the size of number of elements that we've actually stored is equal to the size of the array that we currently have, well, we're going to need to make sure that this thing is at least 1 bigger. Then once we've done that, now I can add items into the size, I can increment it, and I can return the new size of the array. So I'm going to store this thing at the end of the array once I've ensured it's got enough capacity. So if we look at that private method for ensuring capacity, some comments on there that say, all right, it's at least big enough to hold this. Now this is going to take a common algorithm that usually works really well for collections that change size over time. What it's going to do is, if I don't have enough elements, I'm going to either say, all right, let's just make it the default capacity if it's 0. Otherwise, I'm just going to double it in size. Okay. So I'm not constantly, when you're adding elements to array, or an array list, I'm not constantly incrementing a new array of 1 bigger. I'm going to grow this thing in sections to see, and eventually grow it very, very big. It turns out that that's a very good algorithm for performance. So I start at this size, because we often create small collections, say 10, 15, 20 elements. So I don't use a huge amount of storage for that. But I'm going to grow it quickly and see that, if I'm really using something bigger, let's make it a lot bigger so I don't keep allocating every time I add something. And in addition to that, what we're going to see is after we go make that capacity, we are going to need to look back at where we started. This should also copy those elements once we create a new one.
Yeah, I think that's back up at the top of in the previous section there.
Okay, if we go back to add, once we get that in place, it should be underneath here. because the next one is just doing a set of, because items is just that array.
Yep.
So it's already got that. It's going to put it just in that place. So if we pop back to add again, once we do that, ensuring the capacity, that should have to do the, and goes this, if that, do that, and then, there's why. It's inside this, where if I want to set it, you see we're going to build it, and if the capacity that we're setting it to is not the same as what it was, I'm now going to allocate a new array of the right size. And if our array list currently has items in it, I'm now going to go ahead and copy all the existing items in. So every time I grow the array, or the array list, increase its internal storage, I'm going to copy the existing items into the new storage, and then I can work with it in its new size. Good, I'm glad I found that. I was afraid of that for a minute. They were even hiding it from our own code review. Okay, so that's one of the main things there. And then finding things out is merely looking into that array, and we find different things inside it. And basically, this is a wrapper around an array that can grow and shrink itself. And if we look at remove, that'll be sort of our last part of the code review here. So if I want to remove, we'll do a remove at, because it's a similar but slightly simpler. So if the index is not inside our current size of the array, throw an exception. Otherwise, well, we know this is going to be now one smaller, so we'll decrease the size. And then we're going to copy everything from the latter half of the array after the index we're removing back over that one slot. So like if I'm removing the element at index 5, I take everything from index 6 to the end of the array, copy it over so it now takes over the space of 5, and then remove the very last element by setting it to null, and then there we are, we're at the next point. So once again, really hiding that complexity. So now, what we've seen so far by doing this review is in 3 different examples. We've seen classes that were, like if we look at array list, if I go to the end of it, 2,600 lines to wrap and to encapsulate the API that's mentioned by 15 or 20 different public methods that we use every day. Each one of these is in similar size. A lot of that complexity is hidden from us. We need to, as a mental model, know what it does. We don't need a mental model of how does this solve it every day when we're using it. And that's really what we're looking for. So now let's look through and let's, after finishing the code review, let's try to put this in practice ourselves.
Great. So next up is we're going to go over the lab exercise that we're going to have you take a practice at. And with encapsulation is a great concept, but it can be a little bit tricky to really be confident in your encapsulation. And so when you first implement this, it may not be exactly the way that we have implemented it. And that's okay. It's all about practicing this and developing that muscle, developing that skill to be able to encapsulate things fully. So our encapsulation lab, we're going to ask you to create a student, and that student's going to be modeled inside a school. And there are several key considerations we want you to take into effect when you're designing your class. The first one is, does each student must have a name and ID number? The second one would be that the student needs to have a GPA. And when the student finishes the course, we want to be able to update the student's GPA and add a new grade to the history of the grades that the student has.
And one of the things that I want you to work through on these exercises is for each one of these modules, we're going to add some features to this library of functionality about a school, student, and we'll eventually add abstractions for teachers and so on. One of the ways that you should grade your own solutions to these is how much you need to modify as you move forward instead of just enhancing and adding. Those modifications would be things that would slow you down in a commercial application when you get to release 2 and 3. Whereas enhancements mean we're just building the new functionality. So we're often going to want to continue to do that as we do later releases. But we're hopefully not going to want to break apart the things that we've already built. So that's one of the keys that we want to get through, especially starting here with this idea of encapsulation as an object-oriented practice. So with that, you should take a break, try to solve that first exercise, build the code. James and I will be back and we'll discuss one possible solution, and then we'll move on to our next major topic of inheritance. See you soon.